Next, we have Daniel Ramage from Google, and he'll give us a talk on Provably private insights and synthetic data.
Hi, everybody. Thanks for inviting me. I'm not going to be talking specifically about medical or genomic data. I'll be talking about problems that we work on in Google Research, which have some bearing on some of the problems to varying degrees. I'd be happy to brainstorm if anybody's interested. This is work that's joint with a bunch of different people who are named here, because I'm going to be talking about several different years, so several different projects, a bunch of different papers to give you an overview of the kind of things that happen in my lab in Google Research. Peter and Ryan are here today. Yujung was at TPTP. Yeah, let's jump in. So for the kinds of generative AI systems that Google builds, this is the kind of feedback improvement loop we'd like to be able to have. Users interacting with an AI powered feature allows the system to improve by learning from the interaction data in some way that makes a better AI model or a better AI powered feature. And the challenge is that the big models are often pre-trained on public data sets. And of course, we've got our not public in-domain data, which could be very different. In a lot of the medical and genomics settings, that's super, super different. In some cases like email, it might be somewhat different. We have public email from things like Enron, but then there's lots of email that's not public, right? And so when we talk about learning from that interaction data, there's kind of three tiers that I think about. One is getting insights into it. What are people actually doing with these systems? If we know what people are doing with the systems, then maybe we can make the feature better in some way that might not involve sort of changing model weights. You might also directly train on that data, or in a lot of the cases that'll be focusing on in this talk, you might want to get synthetic representative data that looks like that private data in order to inspect or fine tune or train and eval, update your prompts, etc. So the insights slice here, to give you an example of the kind of problem, this is a screenshot of the Pixel Recorder app. It's an app on Pixel that lets you record and transcribe audio in the environment around you. It works on device, and as a result, there's no trace of what happens in the audio or the transcript that goes to Google unless you choose to, click share or something like that. It's an on-device and privacy preserving by default. As a result, the team who built this feature had no idea how it was being used, what kinds of conversations were being recorded, what kinds of topics. So they didn't know if there were any kinds of features they might add that would be able to improve the experience of running this app. So what would you do to solve this problem in the abstract if you could collect all the data? Well, you might take a bunch of the transcripts and then pass them through an LLM to extract some features, right? You maybe have a prompt that you've worked on to say, hey, classify it into these buckets, or maybe you're going to try to learn that prompt in some way so that you can have it automatically discover the kinds of categories or metadata that might be interesting for the problem you're trying to solve. And then you might take that LLM feature extractor and pass it through a DP histogramming mechanism. So ideally, if you're a user of this DP analytic system, which is to say one of the engineers who's trying to make the Pixel Recorder better, you wouldn't be thinking about DP. You would have some auto-tuned DP mechanism here, so you just get out the right histogram values with clipping and noising. And so the flexibility here comes from the idea that as an analyst, I might want to change my prompt at any time, but the DP guarantee, the privacy guarantee, should be independent of that because it's downstream, right? No matter what prompt I put in, I'm going to have a privacy-preserving output. And this is a pretty high utility kind of system. For the purposes of understanding what's happening in this app. But of course, we can't do that because that would require collecting all the data unless we have some sort of isolation boundary here that guarantees that all that processing that I was describing happens in a way that is totally oblivious to the analyst as well as to Google and the system operator, right? We want to be able to prove that no intermediates are actually visible during any part of this phase, and the only thing that's accessible is those DP histograms to the analyst. And that's the system that exists today and that was mentioned on that blog post. It uses trusted execution environments and cryptography and policy engines and open source reproducibly buildable code, transparency ledgers, and a whole bunch of other cool system stuff that I'll flash up on a slide at the end if anyone wants to talk to me about it later, in order to make that set of guarantees. So we really do have a system where everything about that Pixel Recorder transcript is externally verifiable by anyone outside of Google, that's the only thing we can do. We can compute those histograms, and we can't do anything else with the data that goes into that system. And these are the kinds of histograms that come out. So this is the first time that the pixel recorder team had any visibility into how this feature was used. And so these are the real ones. This is a user level epsilon equals 1 for generating the counts, which are the relative box sizing, and a user level epsilon equals 1 with a delta of 1e minus 6 for the label discovery run. Okay, what about actually just training on the data? This I'm not going to talk about too much, but this is an area that my organization's worked in for a very long time. Federated learning with differential privacy is something we've been working on and talked about very publicly with the Gboard keyboard app for Pixel for many years. So in 2022, we had the first production neural network trained with DP. Over time, that we required sort of all LM training tasks to be trained with DP, and they were, in fact, by 2024, all language models trained in Gboard were trained with federated learning and differential privacy, many of which had very tight epsilon, some of which didn't, because the point is the keyboard has to work well. The epsilon you get is the best epsilon you can get for the amount of data you have. So that stuff worked pretty well. But as we transitioned to LLMs, the idea of direct training with federated learning wasn't really relevant anymore. And so we've been thinking a lot about giving teams access to synthetic representative data so that they can improve their products from that synthetic data using the same kinds of pipelines they use to make LLM features server-side in general. And the first paper that we took here was we said, hey, we already have a federated learned differentially private next word predictor model. We could use that as a generator, except that is a poor generator because the next word prediction model on keyboard is only a few million parameters because it has to run super fast. But we thought, well, maybe we don't use that generator directly. Maybe we could sample from a much larger and higher quality generator and then just rescore with the DPFL model. The DPFL model will then subselect the set of things that public large high quality LLM generator does in order to get representative samples. And this works. This was kind of just a reuse of the DPFL model we had already had to be able to sample data, and it improved a bunch of Gboard features, which I'm just going to pass straight through. But as we were thinking about that, we realized there's some limits to this. I'll leave this up while I'm talking. There's some limits to this approach to training, which is that we really want to be able to generate higher quality directly. And to generate higher quality directly, we are going to, we want to be able to find things that are outside the span or underrepresented in that public large model, rather than just rescoring it based on what the DP generator, the DP next word predictor knows. And so we started thinking about ways to do that based on metadata as kind of a key insight for how we could make our generators higher quality. And so this kind of metadata is actually exactly the kind of metadata I talked about in that private insights work, right? Like it could be clusters, or it could be extracted schema that's relevant for the domain, or it could be something that the engineers iterate on. But let's say you've got your private text data and you can extract some metadata from it. You could then make some DPified synthetic metadata, right? And so just having this is going to, if you can generate condition on it, is going to get you something that's closer to the actual distribution of what the private text is than whatever your prior distribution was training your pre-existing large model. So that if you have a DP conditional generator that conditions on the DPified synthetic metadata, which could be one of a variety of different options, you then can generate your synthetic text off of that. And now you've got something that's going to be much closer to the original distribution and therefore more efficient. And so there was one follow-up paper we did was an instance of this where we created the metadata was DP clusters, and the DP fine-tuned generator was a DP. We fine-tuned with differential privacy a much smaller model than the billion scale parameters, but much larger than the 5 million parameter models that we use for next word predictions, wrote this up in a blog post on the Google Research blog about sort of fine-tuning with model with about 100 million parameters to give us DP synthetic data that was much closer in quality to what we would get from a billion parameter model. And this was called controllability and clustering. The follow-up to that work was something that was where we thought about actually making that DP metadata a little bit richer, a little bit not just the clustering, and also adding the ability to, with reinforcement learning, be able to control the generator. So we can say what kind of text do we want to generate, and it would be able to follow those instructions. So be able to generate synthetic representative data that is of the kind that we ask for. Give me synthetic data that looks like this, sort of in a prompt. This works even better than CTCL and works substantially better than the DP fine-tuning. We also applied this kind of idea of conditioning on metadata to the private evolution space in a paper called Maple, where we use AIM to extract the metadata, and then we do a private evolution conditioned on that metadata, which substantially improves upon vanilla private evolution. But both of these techniques are substantially worse than the ones based on the DP fine-tuning approaches. So the DP fine-tuning really does quite a bit better in this problem domain where you have this rich structured data than what you could get with private evolution flavored methods. These are three different metrics. One is the Jensen-Shannon distance metric on the left is how close is it in the topic distribution or metadata distribution space. WAF score is sort of a standard metric for measuring textual similarity based on an embedding model. And this classification F1 score is sort of the ability of the model to accurately predict the next word. So it kind of gets a little bit closer to, are we getting the right token distribution and not just the right topic distribution? And all of these techniques we're working toward being able to run in systems like that private insights system I described, where we are able to have an external verifier flow that allows verifiers to be able to check that only the algorithm we said that we're running is the only thing that can run on the data that's being processed through this system. This is systems level privacy. It's about access control. It's about making claims about what can and can't happen to the data. That might also be interesting for the genomic and health space in situations where you have multiple collaborators who might want to collaborate with each other, but only if you are going to do, a DP synthetic data generation or run some analysis X and not do something else. So this is a system that lets you make really strong guarantees subject to the correctness of the trusted execution environments, which have a whole bunch of issues. That's a different branch of the team works on breaking trusted execution environments and patching up those breaks with cryptography, which I can tell you about if you're interested. So yeah, that's a little view of some of the stuff that's going on inside of Google Research around synthetic data generation and verifiable privacy. There's a list of the blog posts that I mentioned in this paper. The code for this is all open source at Google Parfait. And yeah, thank you.
We have time for one or two questions. And Alex, please come down.
So how does the RL part help?
Yeah, maybe I'll just point that to Peter or Ryan. Do you want to take that?
Yeah, I'm happy to do it. All right. So the issue is you start with a pre-trained model, and that pre-trained model is instruction tuned, but it knows how to follow instructions. When you do the deep fine-tuning, what we noticed, especially at low epsilon, you go to epsilon 4 or below, it loses that instruction following capability. So what you can do is, after you're done DP fine-tuning, you take the model and you try to plug in prompts, generate text that follows some metadata, and you do it a couple of times. You do it n times, and you check the outputs of the model using a much larger public, Gemini model. You pick the best out of n generations. So you do it many, many times. This is a post-processing of an already DP model. So you're not touching the private data set. And you create a data set to do RL on. So you reteach the model how to follow
Generate
instructions.
better.
Yep. And it's just a pure post-processing with the help of a foundation model.
So the reward or whatever metric is based on
Can you,
the output
can,
of the larger
yeah.
model?
So you want to make sure that whatever the model produces follows the instructions in the input prompt. And in this situation, it would be, did the model generate data that has the metadata that was specified in the prompt?
So it's more about learning the prompt instruction.
Okay, let's thank Daniel again.